Hello everyone, welcome back. So today's problem is CYU 8 from the electric current chapter. So the question states that we have an infinite network that is composed of identical batteries and identical voltmeters, like as shown in the figure. Now the reading of the leftmost voltmeter is given as capital V, and the reading of a voltmeter is 1 by eta times of the reading of the adjacent voltmeter to the left. Okay, so they're saying if we take a general voltmeter and its reading is, let's say, some small v, then the reading of the adjacent voltmeter to the right is going to be v divided by eta. So this is what is given to us in the question, and the value of eta and v are given. Now the question is, if the batteries and voltmeters are not ideal, which means they must have some resistances associated with the element, so then we have to find the EMF of a battery. So okay, so that is the question. Give this problem a try, guys, and then check out the solution. Okay, so this is the given diagram to us. So what I'm going to do is I'm going to consider the EMF of the battery as E and its internal resistance as small r, and I'm going to consider the resistance of the voltmeter as capital R. Okay, so now the thing is, the reading of the leftmost voltmeter was given to be V. Okay, so basically what that means is the potential across the ends of these two terminals, which I've marked with red dots, is going to be V. So basically, in short, if I consider all the potentials that are on this lower horizontal line as 0, okay, and why are all of them the same? It's because they're connected by conducting wires and their resistance can be considered negligible. So basically there is no potential drop across these nodes. Okay, so I'm going to consider all these nodes as my reference nodes, and I'm going to give them a potential of 0 volt. Okay, so if I do this, then the potential of this point is going to be V. Okay, and this is the V that was given to us in the question. Okay, now the thing is, if this voltmeter gives a reading of V, then this voltmeter will give a reading of V divided by eta. Okay, so this was also given to us. So what that means is that potential of this node is going to be V divided by eta, and we can write it so on and so forth for all these nodes. We can just keep dividing with eta and we'll get the potential of all the nodes. Okay, so now there are two ways to go about this problem. First is, like, you can number these batteries as battery number 1, 2, 3, and take the kth battery and write equations on that. Or what you can do is you can just write KCL and KVL for the first two batteries itself. I'm just going to write the equations for the first and second battery. Okay, so what I'm going to do now is I'm going to assume some currents. So let's say the current in this branch is going to be I1. Okay, now this is the same current that will flow through the voltmeter as well. So the potential drop across the voltmeter, I can write it as the resistance multiplied by the current, which is going to be I1 into R. So from here I can just directly write V as I1 multiplied by R. Okay, so that's my first equation. Now, as the potential difference across this branch is 1 by eta times the potential difference across this branch, that would mean that the current through this voltmeter will be I1 divided by eta. Okay, and the reason for this is because the resistances are the same, right? Which means if I want to make the potential difference 1 by eta times, then the current has to be 1 by eta times. So now by using Kirchhoff's junction rule, we can say that the current going to the left is I1 and the current going downwards is I1 divided by eta. So the current that must be coming to the junction will be the sum of these two currents, right? If I just name this current as I2 for now, then I can write the equation I2 equals I1 plus I1 over eta. Okay, so this is my second relation. So now what I'm going to do is I'm going to apply KVL in the first loop in the counterclockwise sense. So let's say we start from this particular point, and as we move towards the left, we see a rise in potential across the terminals of the battery, and the rise is equal to E. But the thing is, there is also an internal resistance of R. So we have a potential drop of I1 multiplied by R. So E minus I1 times R. And then there's a potential drop of I1 into capital R across the voltmeter. And then there is a potential rise of I1 over eta times R across the second voltmeter. And this should all add up to 0. Okay, so now if I rearrange this equation and obtain E, it will be equal to I1 times small r plus capital R minus R over eta. Okay, so let's just, I'm just going to call this as equation number 1. So now let's apply KVL for the second loop and let's see what we obtain. So once again, it will be E minus I2 into R minus I1 over eta times capital R plus I1 over eta squared times capital R. So once again guys, the current in this branch will be I1 over eta squared, right? So moving in this direction, we see a potential rise of plus I1 by eta square times R, and this should be once again equal to 0. Okay, and from here what we get is E equals I to R, and for I2 what I'm going to do is I'm going to substitute this value so that we get everything in terms of I1. So it'll be I1 R times 1 plus 1 over eta minus I1 times R over eta plus I1 times R over eta squared. Okay, so once we take I1 common, this is the factor that is being multiplied. So I'm going to just call this as equation number 2. So now if we look at equation 1 and equation 2, the factor multiplied is different for both of them, right? But the other quantities are the same. So it's quite obvious that this quantity has to be equal to this quantity for both of these equations to hold, right? So yeah, so we can just directly do that. So we can just directly equate these two terms. Okay, so there was a slight mistake here. So this would be actually a plus, okay, not a minus. And this would be a minus. Okay, and after solving this inequality, we get something like this. So small r over capital R turns out to be eta minus 1 whole squared divided by eta. So this is the relation that the ratio of small r by capital R has to satisfy. Okay, so now the thing is we can pick up relation number 1, substitute the value of I1 into this equation, substitute the value of small r using our ratio, and let's see what we get. Okay, so after substituting the value of I1 and the ratio of small r by capital R, so it just simplifies as, the EMF just simplifies as V times eta minus 1. So, and that turns out to be 1.5 volts. So yeah, that was the answer to this question. So that's it for this video, guys. If you enjoyed the video, do like, share and subscribe. And that's it. Thanks for watching.